Hello, Stormwater designers. Welcome back to Clear Creek Solutions instructional videos. And today we're going to be going over a project that I found in the SWM knowledge base that someone posted here. This is effects of soil texture and saturation on infiltration. And so this individual here states this example model is intended to highlight the effect of variable soil texture and degree of soil saturation on hydrologic response using the green amped infiltration method in SWM. The model features a series of similarly shaped subcatchments with common terrain and surface cover parameters, but with different soil characteristics. All subcatchments are subject to the same 1-inch rainfall event, or 12 inches per hour for 5 minutes. Evaporation is not represented in the model, and the common parameters include an area of 1 acre, a slope of 1%, 0% imperviousness, a Manning's roughness factor of 0.4, a 0.7-inch depression storage, and a sub-area routing outlet. 3 soil textures are represented, the sand, loam, and clay, and each texture was assigned common capillary tension and saturated hydraulic conductivity, or KSAT values, but with a range of initial deficit values. The figure below shows the arrangement of subcatchments by texture in 3 rows and by degree of saturation in 5 different columns. Subcatchment names reflect the degree of saturation ranging from fully saturated, so 100%, to dry, 0 saturation. So we have this image here, which shows sand 100% in the top left, and then going down for, in order for each of the soil types, from sand, loam, and clay, from 100% down to 0%. The sand, the tension is 2-inch, KSAT is 4 inches per hour. The loam, the tension is 3.5 inches with a KSAT of 0.15 inches per hour, and then a clay with tension of 12 inches and a KSAT of 0.01 inches per hour. The initial moisture deficit parameters are shown in the table. These values represent the available soil pore volume that can be filled with infiltrated rainfall. A fully dry soil, i.e. 0% saturation, is available to hold the effective fillable/drainable porosity, defined in this case as the difference between the soil porosity and the volumetric water content at its wilting point. For example, a sandy soil with porosity of 0.437 and volumetric water content of 0.024 at the wilting point would have an initial deficit of 0.437 to 0.024 or 0.413 at 0% saturation. The initial deficit would be 0 at 100% saturation and would vary linearly between these two extremes at other saturation levels. So we can see the initial deficit by degree of soil saturation with the texture going from 100% to 0, and then the sand, loam, and clay, and each of those ascending values. Applying the infiltration result for sand 100%, loam 100%, and clay at 100% will show that fully saturated soils infiltrate at a constant rate of KSAT until all the rainfall is either infiltrated or become runoff. We can see that by the graph here. The sandy soil takes about 15 minutes for 1 inch of rainfall to infiltrate. There is no runoff. Running the model for a longer simulation period would confirm that fully saturated loam and clay soils take about 6.2 and 78.5 hours respectively. The pie charts seen below compare the hydrologic water budget among the 3 soil textures. So 100% saturated sand is almost all infiltration, no runoff. 100% saturated loam is a bit of runoff, but mostly infiltration, and then saturated clay has much more runoff and a lot less infiltration, obviously because of the structure of the clay soil. Fully dry soils infiltrate at a rate between the rainfall intensity and KSAT reduce asymptotically toward KSAT until all the rainfall has infiltrated or become runoff. The sandy soil takes about 6 minutes for rainfall to infiltrate, and the loam and clay soils take about 1.7 and 15.5 hours respectively. All the rainfall infiltrates into the sand and loam soils and 97% into the clay soil, i.e. 3% runoff. We can see that with the graph here, the infiltration and then over the elapsed time. None of the sandy soil scenarios yield runoff, and only the 75% and 100% saturated loam soils yield runoff of 1% and 7% respectively. All the clay scenarios produce runoff, obviously, and the proportion is shown in the pie charts here. So it's just showing the performance of these different soils given a certain saturation amount. Obviously with clay, we're going to get more runoff than any other soil because the texture and the grain size of the different. So this project is an interesting study on how different soil layers will react given KSAT factors and rainfall and what kind of runoff they'll produce. Obviously in that continuous simulation model, it'll do a better job of determining the amount of runoff given the different time steps that are provided. This is an interesting study using EPA SWM. You can download the IMP file here, the specific project, but this is an interesting analysis done by this individual. Let me know what you think about the different saturation and runoff of these soil layers, what maybe we could look at in the future. Thank you for watching this video, and we'll see you guys next time.